also would like to show that we have this thing called statistical compendium, right? And I think many of you have seen this before. Can I just... Lovely, everything is in Dutch and then followed by English, but I'm sure you'll figure it out. There are 11 chapters in the statistical compendium. We'll provide it to you on the exam. And here's chapter 5. Chapter 5 is the chapter on estimation. Every formula that you'll have to use in order to solve anything regarding estimation can be found in chapter 5. Right? So you don't have to learn all these formulas, and you can just check in the compendium itself. All right. Now, the two most important things that we'll do during these lecture series is estimation, which is what we do today, and hypothesis testing. They're closely related. We'll start with estimation. And estimation is basically answering these kinds of questions, like how many of my potential customers would be interested in this new product, or how many customers are satisfied with my product or service, stuff you will have to deal with during this project. How much do people want to pay for my product? And all of these things we can't know for sure. There's no way of knowing for sure, even if we would ask everyone in our population, every customer, we would ask them what they would like to pay, and they would all give us an answer. They'll probably change their mind the next day, or not even remember what the answer is that they gave. So there's always some variance in that, even if you'd ask the entire population. So there's always a little bit of an error, which is why we are estimating the answer. We're saying it's probably between this and this value somewhere. It's an estimation. Now, we've done this last time. If we asked 10 people whether they're interested in a product, and 2 of them say yes, then we can conclude from that that roughly 20% of the people are interested in this product. Similarly, if we ask 100 people and 20 answer that thing, and for 1,000 people asked and 200 answering, the conclusion is every time is the same thing. Roughly 20% of my population will be interested in this product. But now I want to be more specific. I want to be estimating between what values the amount of interested people are going to be. Like, I want to say with 95% confidence, or 95% chance that the amount of people that are interested is between 10 and 30%. Now, we can do this pretty easily after this week by estimating this, and we'll need some formulas for that. I'll go into that in a bit, but for example, if I only ask 10 people and I want to be 95% confident about the values I give to the company, then if I only ask 10 people, it turns out that between 10.1 and 29.9% of the people will be interested, which is a huge spread, a huge margin. Don't really know how many people are going to buy my product now. It's either somewhere between 10 and 30%, which will make a big difference in the amount of revenue this new product will give me. So if I ask 100 people, this interval shrinks. It'll become between 16.9 and 23.1%. And if I ask 1,000 people and 200 people exactly answer that they are interested in the product, now I have a confidence level of 95%, so I'm 95% confident that my actual customer base, the amount of interest is between 19 and 21%. So asking more people gives me a smaller interval or bigger accuracy, or better accuracy, I should say. Bigger is a bit confusing because the accuracy actually shrinks. But that's better, right? We're more accurate that way. And there's a interplay between these things, between how confident I want to say something, how large or how precise my accuracy will be, and how many people I ask. So there's this interplay between these three variables. Now, how do we do an estimate? We've also talked about this last week a little bit, where if I wanted to know the voting behavior of Dutch people, then we asked the question, how many people should I ask about their voting behavior? And some of you said 1 million. Most of you were not okay with me asking just 10 people. But it turns out that between 300 and 3,000 people is already enough to say a lot about the entire population of the Netherlands. So we're doing a sample, we're asking a specific set of our population to give us an estimate over the entire population. Now this is important because there's a very distinct difference between a sample and the population itself. Now I can have my population and it's distinctly different from my sample. My sample will tell me something about my population. And in this sample I can do some statistics. I can measure some values and determine some variables that are going to help me with that. For example, if I do a sample, I ask 5 people here about their length. Then I've done a sample. I can average that sample. I can average the length of those 5 people to give me some prediction about what the average length of people in this room is. And we call that X with a bar on top. The bar means the mean or the average of a variable. And X is the variable I'm interested in. In this case, it's length of people, but it also might be price they are willing to pay. Any continuous variable. Yes? And this average length of my sample, I'm going to use that to say something about the average of the entire population. So if I want to know the average length of everyone here, the easiest way to do it would be asking everyone, note down all the lengths, and from that calculate the average length, right? But if I wanted to do it for all students of Fontys, I'm not going to ask them all. It's too much work and I'm lazy. So instead, I'll ask a group of people and use that value that I get to estimate something about the actual population length. So I get, let's say, an average length of 175 centimeters from the few people I've asked. That can tell me something about the actual average of the entire population, which then is somewhere between, let's say, 170 and 180 centimeters, depending on how confident I want to be, and depending on the standard deviation of my population. Now, this is perhaps the most difficult part of this topic, which is what this standard deviation is. We use a sample average to estimate something about the population average. Similarly, we can have a sample standard deviation S and use that to estimate something about the standard deviation of the population itself. We can use standard deviation of our sample, which is S, to say something about the standard deviation of our population. But while we normally will use a sample average to estimate something about the population average, we will need to either use the standard deviation or the sample standard deviation to make this estimate. Because we can use either the sample standard deviation or the population standard deviation for this, we usually don't use the sample standard deviation to estimate the population standard deviation. This estimation doesn't really happen that often, because we can either have this and use this in combination with this to estimate this, or we have this and use them together to estimate this. So this estimation here is not used very often. Instead, we use something like that or something like that. One of the two. We only need one of the two. Now, a small problem arises from the fact that if we use the sample standard deviation to estimate something about our population, we're going to make an error, because the standard deviation in our sample will definitely be different from the standard deviation in our population itself. Because of that, we will need to use a different test or a different distribution of numbers. How that works I'll get into a bit later during this lecture. But for now, it's important to note that we either need this or this. We need some standard deviation in order to make an estimate of the sample mean to the population mean. Right? So in the end, we basically only use a sample to say something about the population average. Now lastly, there's something like when I am interested in the length of the average person, I'm looking at a continuous variable. But if I want to know what percent of you was on time for this lecture, or what percent of students on average is on time for a lecture, you're either on time or you're not. So there's a discrete set of possible outcomes, and that percentage that I'm interested in is based on a whole number divided by another whole number. Let's say there's 20 people here, 18 of you were on time, then that number, that percentage I'm interested in is 18 divided by 20. It's a percentage, but it comes from discrete values, and in that case I am talking about the values p and pi. Now, there is a lot of useless information in my head which I'd love to share with you. Unfortunately, I have no idea why we use these variables for this. I have no idea why we use the letter. Well, I have an idea of why we use the letter p and pi, but it's not very strictly historical based, in my mind at least. The idea is that a percentage, when I talk about a percentage, when I'm interested in a percentage, I'm interested in some discrete distribution. I can either be interested in the amount of students that are on time, or I can be interested in the length of the average student, but there's never any situation where I'm interested in both at the same time. Hence, we either use a sample mean to estimate the population mean, or we use a sample probability, percentage chance, to estimate the population probability. Yeah? Either this or this. Now, I usually break these up into two different things, because when we're talking about a probability of something happening or not, or percentage, we don't need standard deviations. So standard deviations only occur when we're talking about averages. So, the important part is there are symbols on the right. Those symbols pertain to my sample, and there are symbols to the left, and they pertain to my population. The easiest way to keep them apart is that these are letters from our alphabet. These are letters from the ancient Greek alphabet. So the Greek letters pertain to the population, the regular letters pertain to a sample, and pi is sort of the equivalent of p in the Greek alphabet. Mu and x, not really, but I don't know, give it a break, it's fine. S and sigma are quite similar again as well. And these are the only things we need in order to do estimation. We either estimate a population fraction from a sample fraction, or we estimate the population average from a sample average. Now, to do this estimation properly, we could use the help of some extra variables. Namely, we have something called accuracy, which we denote by the letter A, and confidence level, which is usually a percentage, and we denote that by the letter alpha, which is similar to the letter A, but then Greek. And it you can find it by doing 1 minus the confidence percentage level you're interested in. So let's say you want to be 95% confident, then my alpha is 0.05. Now it's not always entirely true, but we'll get to the distinction, well, in the next slide it seems. Now, the idea is that if I have my sample average, I will use that together with my population standard deviation to get some mu, which is between these values. I want to estimate my population average. My population average will be between my sample average minus my accuracy and my sample average plus my accuracy. So let's say I have a sample average of 175 centimeters. We measure 5 people here. Each of them has a specific length, and if we average those lengths, we get a length of 175 centimeters. And let's say I calculate my standard deviation from that and use some nice formulas, which we'll see in a bit, to calculate an accuracy of 5 centimeters. It means that my interval for the population average will be between 170 centimeters and 180 centimeters. And let's say I want to be 95% confident about it. This 95% confidence and the standard deviation will determine my accuracy, and how that will happen we'll see in a bit. But let's say I want to be 95% confident. Turns out that from my sample average, I measure 175 centimeters. I use that to estimate that my population average is between my sample average minus my accuracy and my sample average plus my accuracy. 170 to 180 centimeters. That is how we do estimation. Now, how to get these values specifically, we need to use formulas. I want to use one which is relatively, well, we've used it a lot last year, so it should be relatively simple. And I want to shortly derive how you get to it, so that it at least links a bit to last year's, unless you've all forgotten exactly everything about last year, then you can just assume the formula as well. Oh, there's a nice example here as well. You can figure it out. When we're talking about these kinds of distributions, samples and population, we're usually talking about a normal distribution. If, for example, I measure the length of an iron bar produced in the factory, like the example on the previous slide, then usually we assume that's normally distributed. Like a large deviation from the average has a very small probability, but small deviations from the average have high probabilities. That's basically what characterizes a normal distribution. Now, here are the formulas that we can use to determine these boundaries for which we get our interval. So effectively, we have a normal distribution. Normally, we put mu in the middle, and then in the jargon we used last year, we wanted, for example, to know, let's say my mu is 175 again, and I want to know what is the probability that when I take a random person off the street and ask them for their length, that their length is larger than 180 centimeters. That was what we did last year. We said, here's a population average. We know the average from the population. I pick a random person from the street and ask, what is the probability that he is either a length of 180 centimeters or more? And then we calculated that probability using z-values, and we said that z-value bigger than 180, we had to reform it to the standard normal distribution, which we did by using this formula. And now we can see that if we just rearrange this formula, if instead I call this my right bound, then this changes to GR. If I rearrange this formula with exactly this formula, with one small exception, and that is that I don't get my sigma divided by square root of n, but the mean standard deviation of a distribution with multiple the same distributed numbers in them gives us that factor. So instead of looking at one person, we're now going to flip it around. We have an average of multiple people, we need to calculate the average standard deviation from that and get this formula. Rearranging it gives us these two formulas, and then we can rearrange the whole normal distribution and instead of putting mu in the middle of my normal distribution now, I want to put the sample average in the middle of my normal distribution, because my sample must be normally distributed as well. And now I'm going to call this point x plus a, this point x minus a, and this is my confidence level. I want to be, for example, 95% confident. Then this area must be 95% of the area under the curve of the normal distribution. And then I can calculate from that what my accuracy is, which is basically just this length. And that gives me my bounds GR and GL, which gives me the interval for mu that I'm interested in. And we do this because we're now looking at examples where we don't know the population average. Instead, we can determine a sample average, and from that want to estimate the population average. So we can no longer use the stuff we learned last year. We'll have to invert that and work backwards from the sample that we have. So instead of having a population average known and calculating the probability of having this one person deviate from that or not, instead we're flipping it around. We have a few people we asked, a few data points, and from that we want to give a bound on the population average. Now, what we need in order to do that is we either need to know the actual standard deviation from the population or the standard deviation from the sample, but we'll get into that in a few minutes. Let's for now assume we know the standard deviation of the entire population. We get some sample average. We need to know how many people we've asked. It's important for this factor. And then we need to know how confident we want to be. This will determine the z factor that is given here. Because again, we want to calculate this value now, which is complete opposite of what we did last year. Now, the mu will then be between my right bound and my left bound. The formulas are here, which effectively means that mu is between my sample average minus my accuracy, or my sample average plus my accuracy. Thus, my accuracy is given by z times sigma over square root of n. This little part here is exactly my accuracy. It's how far away my right or left bound is. And we assumed we knew the standard deviation. Standard deviation is known. The amount of people we've asked or our sample size is known. And from our data points, we've calculated a sample average. We know how confident we want to be about anything we're going to say. Let's assume that's 95%. From that confidence level, we can determine the value of Z. Yeah? So the Z value, the Z-score, is something you have to read out from the tables of the statistical compendium. Now, let's do an example. And before we go over the example, I want to just illustrate how this makes sense. Because I think some people might be wondering how it's possible that you have no idea about the average of the population, but you would know the standard deviation of the population, because that's weird, right? I mean, to me that sounds weird. If I know the standard deviation of the population, I then know how an average sample from that population deviates from my average. So how can I not know this but know that? It's weird. So that's why we do a battery example. Let's say I have a factory and I have invented a new type of battery. Yeah? Maybe it is similar to my old batteries but requires cheaper components. So I want to now produce these because it's cheaper for me, gives me more profit. What I know is that I have a new way of producing this battery, so I don't know how long these batteries are going to last. But I do know, for example, that they are lithium batteries. We use lithium for the core component of the electrical transportation, and I know the half-life of lithium, so I can actually deduce a sample, a population standard deviation from those factors, right? If we only change a few components, it might have an effect on the lifetime of the battery, but the standard deviation might be completely dominated by one of the components I use, which I haven't changed. So that's an example of why knowing the standard deviation of an entire population is possible before even knowing the average of the entire population. Now let's say we are in this case where we want to know mu, I want to know the lifetime of all my batteries, the average lifetime of all my batteries. I want to be able to put something in the box when I ship it to the shops. And on the back of the box it says, this battery will last you roughly 45 hours, let's say. I want to put that on the back with some certainty, without people then taking out 10 of those batteries, testing them, and finding that it's only 40 hours instead of 45. Okay? So we're going to do a test, take a few of these batteries we've produced, let's say 100, and from those 100 batteries, we find that the average lifetime is 46 hours. Now, to do this calculation, to give us an estimate of how long the entire population of batteries on average lasts us, we need to find the Z value, the sigma value, and N. Now what is N in this case?
100.
Sorry?
100.
100. So N is just our sample size. We can put this here. Big N is the entire population. Small n is the sample. In this case, it's 100. Now, our standard deviation for the entire population is known, is given, because we've tested lithium batteries for centuries. We know the standard deviation of a specific form of lithium battery, but our batteries use a few extra components which have an effect on the average, but not on the standard deviation. Happens. Now, last thing we need, we have the sigma, we have the square root of n, or we have n. We can calculate the square root, that's simple. Now we just need z, or z value. How on earth do we get that? Now, go ahead.
Obviously, check the table for 2.5%.
Exactly. First, we do the confidence level is 95%, so we have to determine some alpha. I normally will tell you that the confidence level is some percentage, but some textbooks or literature use simply an alpha value. They say this is the average given this alpha value. So that's why you need to both learn confidence levels of 95% and what that means for the alpha level. And in this case, alpha is, well, it is 0.05, but that is because we want some interval between two values. That means we're testing, or we want to calculate the probability of being in this area and the probability of being in this area. And we want that total probability to be 5%, because this is 95%, which means this is 2.5% and this is 2.5%. That's on 95% confidence level. We want to be confident for 95% that it's in this area and only 5% that it's in the outside areas. Normal distributions are completely symmetric. That is how we've constructed them, which is why each of these areas is 2.5%. My Z table only gives me one of these bounds. So I need to take 2.5% as my alpha. Alpha is 0.025, which leads to a Z value. Now, it might have been a while since we've worked with the Z tables. Here's a little screenshot from the actual statistical compendium. It's a normal distribution. It says this in English as well in your statistical compendium, where we're saying the probability that our case that we're interested in is larger than some value for Z, and this probability needs to be 0.025 in our case. That's what it's saying. So we want our data point, this one, to be bigger than the cutoff value, which is there, and the probability for that happening is exactly 2.5% by construction. Yeah, we're working backwards compared to what we did last year. So instead of calculating the size of this area, we say we know this area, it's 2.5%. What is now this value? So we know it's 2.5%. What is this value? And the way we did it last year is we calculated the Z value, and then in this table we looked up, for example, we had a Z value of 1.645. That was one we often encountered. If the Z value was 1.645, I would look up 1.6 and then 45, 1.645 give me exactly 5%. That was how we did it last year. Now we do it the different way around. We know the probability is 2.5%. So we look up in this entire table, where is 2.5%? Now keep in mind, these probabilities strictly decrease. So here's 50% probability. And if I just follow the list, I see that the numbers only decrease. So it's not like a random guessing game, where's my probability of 2.5%? You can just follow the numbers until you reach 0.025. Now, I know this is the probability I'm looking for. What is the Z value that corresponds with it? And we can just read off. It is 1.96. So our Z value with a probability of 0.025 is 1.96. Now, I am telling you, you don't have to learn all these numbers in your head, obviously. This one though, should try. Should try and keep this one in your head. This one as well. These are values that come up a lot. Because we're doing it the other way around this year, where we are imposing a specific area, which is often going to be 2.5% or 5%, which has the corresponding Z values of 1.96 or 1.645. Now we're going to have some other values, 2.2, it's going to come up as well a lot. It is useful to know these numbers in your head so that when you're looking for these numbers in the table and you see 2.5%, 1.96 comes up, you're immediately, oh, right, that's one of the normal numbers we always see. I must be doing something right or something good. Again, you don't have to learn these from the top of your head, but then you'll have to look it up in the table every time, which takes time. So, coming to the exercise classes, the workshops, often you'll automatically start dreaming about these numbers. Hopefully not, but it happens for me, so it's going to happen for you at some point. Now, when we have all the values we need, we just have to calculate the interval. The interval was mu was between x plus a and x minus a. A is given by z times sigma over square root of n, which in our case 1.96, sigma was 5, n is 100, so this is something like this. Obviously. Now, my A is 0.98, which means my accuracy is 0.98. My accuracy is exactly this little bit. That's the part of my interval which we define as the accuracy, which means that this bound here is 64.98, and by construction the other bound is equally far away, and it's 45.02. Now that's what this says here at the bottom. We know from this little test that we did, we examined 100 batteries, which is quite a bit of work obviously, but let's say this company produces 100,000 batteries, so checking 100 is then more reasonable. From this little test we can conclude with 95% confidence that 100,000 batteries will have an average lifetime of 45 to about 47 hours. Now that is essentially the only thing you need to do. Estimate that population average. Right. Any questions so far? No?
Just a question. So, is there any case where we're going to have to find the standard distribution of the population and the standard distribution of the mean? Will we have
no.
to find both? Ever? Okay.
Never. You mean this and this?
No, I mean like the population, the mean population and the standard deviation population. Like, will we ever have to find those two in the same issue?
Oh yeah, you could do.
Okay.
You could have a sample where you have to calculate the average yourself. That gives you the mean, and then also calculate the standard deviation from that sample.
Okay.
Yeah.
Thank you.
Yeah, that's definitely possible. All right. I've been talking for quite some time. Let's take a break. We do have plenty more to tell.